So in this video I'm going to talk about the solutions for the problem which appeared in Thermal and Statistical Mechanics in GATE 2013. The first question is, if Planck constant was 0, then the total energy contained in a box filled with the radiation of all frequency at temperature T would be. Okay, so here in fact the answers and the options that are given to us, it's the D in principles, and it's not mean related to the total energy inside the cavity, but where it's related to average energy basically. Okay, so let's try to understand how we can arrive at this final conclusion. So energy, the average energy in case of black body radiation that is given by E, and that is equal to the mean number of photons, you can say, that is Nk, and then the energy associated with the one single photon, that is h cut omega. Okay, where Nk, that's the mean number, it's also called as the occupation index. Okay, so Nk is equal to, for the photon, it is equal to 1 upon exponential h cut omega upon kt, where k is the Boltzmann constant, minus 1 multiplied by h cut omega. Okay, now from here we notice that if the Planck constant goes to 0, so that means if h cut goes to 0, so then we are having the average energy of the form 0 by 0 in this form. Okay, so therefore we can apply L-Hospital rule to evaluate the quantity, the average energy. Okay, so that means, so what we are going to do is we are going to take the derivative of numerator and separately, and that of denominator separately, and then put the limit h cut approaching 0. Okay, so let's see. So in that case, by applying that rule, the average energy, that is equal to limit h cut approaching 0. Okay, and then h cut omega upon e power h cut omega upon kt minus 1. So by applying the L-Hospital rule, this becomes equal to, this is equal to limit h cut approaching 0, differential of numerator with respect to h cut, so that will give us omega. Okay, now the differential of the denominator, that is e power h cut omega upon kt, and then again the differential of the exponent with respect to h cut, so that will give us omega upon kt as h cut goes to 0. Okay, so as h cut goes to 0, so exponential, this term, it will reduce to unity. So okay, so omega and omega, that will cancel with each other, so finally we are left with kBT. So it's not the total energy, but it's the average energy. Okay, so therefore option D is the correct one here. Let's continue with the next problem. So it's related to the first order phase transition. The question is, across a first order phase transition, the free energy is, okay, so we have to identify the the correct option here. So for this purpose, I will try to take the example of the change in Gibbs free energy. So that is equal to minus s dt minus p dv. Okay, so from here the entropy, that is equal to minus dg upon dt. That's the first order derivative of the Gibbs free energy with respect to temperature by keeping volume constant. And from here, this implies that the entropy per particle, that is S, that is equal to minus dg by n upon dt by keeping volume constant, and that is equal to minus curly mu by curly t by keeping volume constants. Okay, so we note that the entropy or the entropy per particle, both of these are positive quantities. These are positive quantities. Okay, so that means if we talk about the variation of the Gibbs free energy, or the variation of the mu, this is mu, g by n, that is mu, that's a Gibbs free energy per particle. Okay, to make it a positive quantity, we have to ensure that dg by dt, it is a it's having a negative slope here. So for instance, suppose we are talking about this transition here. So let me take an example of the ice water system, or some other system having positive. It's an example of a system which expands upon melting. Okay, so P versus T diagram here. So suppose I'm talking about movement from solid phase to liquid phase, solid to liquid phase here. Okay, so let me label this point, the corresponding point here on the temperature axis T naught. That's a transition point when we are moving across the solid to liquid boundary. Okay, so here if I want to plot the variation of Gibbs free energy with respect to the temperature, so it's the temperature that is changing here at constant pressure. Okay, so because to make the this entropy or entropy per particle as a positive, so G versus T variation, it should be negative. Why? Because here we are already having a negative sign here, and to make the entropy as a positive quantity, dg by dt, it should have a negative slope. So that means, so let me draw a line here that corresponds to T is equal to T naught. So it should be something like this. Okay, so I'm drawing here two lines, so I will explain in a moment. Okay, but so both of these two curves, they are having negative slope. Okay, so it's a, you can say G versus T, or you can write it G by N, that is equal to mu. Okay, so here for temperature smaller than T naught, so it's the, if you just take a look at this point. Okay, so below this temperature it's a solid phase that's stable, and above this temperature it's a liquid phase that's more stable. So that means here this corresponds to G solid. Below T, for T less than T naught, solid phase is more stable. So therefore this will have smaller values of the Gibbs free energy. Okay, and this will corresponds to G liquid. Okay, and when we have crossed the boundary, the transition temperature, so in the other side it's the liquid phase that's more stable. So this, the line with the lower Gibbs free energy, this will corresponds to liquid, and this will corresponds to G solid. The point is that it is the lower Gibbs free energy, I mean the system which is more stable, that will possess a lower value of the Gibbs free energy. Same is true for the chemical potential also. Okay, so if you draw a diagram here, instead of talking about the Gibbs free energy, we talk about the chemical potential, which is nothing but Gibbs free energy per particle. Okay, so we will have a situation like this. Okay, so this is mu solid, and this is mu liquid. Okay, so that means if you just take a look at this, so it's the Gibbs free energy, it's a Gibbs free energy for the solid phase, but at this point there is a change of the slope. Okay, so there is a slight a very small discontinuity will appear there, but in overall it appears to be a continuous function of temperature. So therefore across the first order phase transition, the free energy, it's not proportional to temperature, and it's also not discontinuous function of temperature. It is a yes, it is a continuous function of temperature, but its first derivative. What is the first derivative of Gibbs free energy? So that is entropy. So entropy at the transition point, that will look like this. Okay, so entropy at the transition point, if I plot the entropy, which is minus dg by dt. Okay, so that is equal, so here at the transition point it will look like this. Okay, this is the solid phase, and this is the liquid phase. Okay, and this is the temperature T naught. So at transition there is a discontinuity in the entropy, which is the first order derivative of G. Okay, so by S, that is equal to minus dg by dt. So this is going to discontinuous at the transition temperature. So therefore C is the correct option here, such that the first derivative with respect to temperature is continuous. No, this is also wrong. Okay, so C is the correct option here. So let's take a look at the next problem. The statement is two gases separated by an impermeable but movable partition are allowed to freely exchange energy. So we are having a impermeable. Impermeable means so the number of particles they cannot cross. Okay, but it's a movable partition. Okay, so it's a movable partition, so that means volume exchange is allowed, and they can also freely exchange energy. So at equilibrium the two sides will have the same. Okay, so let's try to understand this problem. So this is basically a question from the statistical mechanics. Okay, so let's see how we can understand this point. Okay, so suppose we are having a one big container, and inside this container we are having a one membrane which is impermeable. So this is a membrane, this is impermeable. Impermeable mean particles cannot cross it. Particles cannot cross it. Okay, but it's given that it's movable, so it can move in the either along the right direction or left direction. It's movable. So movable mean, okay, it's movable. So that mean volume exchange is allowed. Volume exchange between two subsystem is allowed. Volume exchange allowed. It's also given that the these two gases they can freely exchange energy. Energy exchange is also allowed. Energy exchange is also allowed. Okay, so now let's see how what's going to the final answer. So when we talk about such kind of system, okay, so if energy exchange between such two systems is allowed, then the composite system in equilibrium state, then the composite system that we obtain, composite system in equilibrium will have a common temperature. Okay, so let's say T1 is equal to T2 and that common temperature is T. Okay, now the second point, when the volume exchange is allowed, when volume exchange is allowed, then we say that after the volume exchange has taken place, and again these two systems they are in equilibrium, when volume exchange is allowed and two gases are in equilibrium, Librium, sorry. So then in equilibrium we will have the pressure of these two gases system, they will be identical. Let's say P1 is equal to P2, that is equal to P. And the third point is that when these two systems they can exchange the particles, when particle exchange between these two systems is allowed, then the equilibrium ensures that equilibrium between these two systems and show that the chemical potential of the first system that is equal to chemical potential of the second, and that is equal to, let's say, mu. So these are the three different condition that we can try to understand in a different way. In principle, the mathematical solution for this problem exists, but that will make this this a very lengthy affair. So I'm providing here the final conclusion. So just based upon these three important points, we can draw the conclusion. For instance, in the present case, we are having the volume exchange as well as the energy exchange. Okay, so that means the energy exchange ensure that T1 is equal to T2. So that means the final temperature of these two systems that's equal to identical. Okay, that's T, let's say, common temperature. The volume exchange ensure that P1 equal to P2, and that is equal to, let's say, P, common pressure P. So therefore, because for the given constraints, the final temperature and pressure of these two systems, they should be identical. So pressure and temperature, so that means option A is the correct one. Okay, so let's try to understand under what condition we will obtain the option B. So volume and temperature. So volume and temperature no, volume, no, not the volume and temperature. Okay, the pressure and volume, so they no, that's also not the criteria. Volume and energy, that's also not the criteria. Criteria is in terms of temperature, pressure, and the chemical potential. Okay, so therefore option A is the only correct one here. The remaining three, they are wrong. So let's take a look at the next problem. The statement is the entropy function of a system is given by. So we are given the expression for the entropy as a function of energy E, that is equal to A E into E0 minus E. Okay, where A and E0 are positive constants. So A and E0, they are given to be positive constant. Okay, the temperature of the system is, okay, so we can because we are given the expression for entropy in terms of energy, so we can correlate the temperature with the entropy energy by making use of the thermodynamic potential change in internal energy du, that is equal to TdS minus PdV. So from here we notice that T, that is equal to du by ds by keeping V constant, or sometime, because here it's the E notation used for the energy, so I will make use of this notation. That's dE by ds by keeping volume constant. So from here I notice that 1 by T, that is equal to ds by dE at constant volume. Okay, so by making use of equation 1 and 2, so the expression for the 1 by T, so that is 1 by T, that is equal to ds by dE. Okay, so that is equal to A. So the expression can be ds by dE. So that means A. So this comes. So okay. So let's treat them as two separate function. Okay. So the first function and then the differential of the second. So that will give me a -1 here. Okay, and then plus the second function E0 minus E multiply by differential of the first one with respect to E, so A. Okay, so this is equal to minus AE plus A E0 minus AE. Okay, or this is equal to A E0 minus 2A E. Okay, and after the rearranging the terms, T, it comes out to equal to T, that is equal to 1 upon A, I can take outside, A into E0 minus 2E. So therefore from here, from this expression, we notice that when E0, it is smaller than 2E, so in that case temperature, it becomes a negative quantity. Okay, so therefore the correct option here is A. So because the temperature, it could have a negative values for certain energies. Let's take a look at the next problem. So the statement is, consider a linear collection of n independent spin half particles. So we are having n independent spin half particles, each at fixed location. So these are at fixed location. So that means we can treat them as distinguishable. We can treat them as distinguishable. Okay, the entropy of this system is, okay, because we are having a system of n distinguishable spins, and each spin is having two possibilities. Okay, so each spin has possibility equal to 2. So what are these possibilities? Basically, either it can have plus half value or minus half value. Okay, so now suppose I'm talking about the first spin. So for the second spin, it's also having two possible orientation. Third spin is also having two possible orientation. So this way the nth spin will also have how many orientation? Two orientation. So okay, so because the orientation of each spin, it's completely independent from the orientation of the another spin, so total mean the total possibilities are mean the multiplication of all these n terms. Okay, that is equal to 2 power n. So that basically represents the number of microstates corresponding to this system. Okay, so that means the total the entropy for this system is equal to S. By making the Boltzmann definition of the entropy, S is equal to Kb ln omega, that is equal to Kb ln 2 power n. Okay, so that means S is equal to n Kb ln 2. Okay, that's the answer. Okay, so in fact we can also obtain this this result by making use of the fact that the total number of spin orientations, that is omega 2s plus 1 orientation for one spin, that is 2s plus 1 orientation for one spin, and for n spin it's going to 2s plus 1 power n, and okay, so that is equal to 2 power n. Okay, and D is the correct option here. So let's take a look at the next problem. The question is the number of distinct ways of placing 4 indistinguishable walls into 5 distinguishable boxes. So here we are given n is equal to 4 indistinguishable walls. Okay, and the number of distinguishable boxes are, that's G, that is equal to 5. These are distinguishable. Okay, so this problem is identical to distributing 4 bosonic particle in 5 different energy level, and the corresponding number of ways, that's omega, that is equal to n plus G minus 1 factorial upon n factorial into G minus 1 factorial. Okay, so that is equal to 4 plus 5 minus 1 factorial divided by 4 factorial and 5 minus 1, that is 5 minus 1, that is again 4 factorial. Okay, so that is equal to 8, 7, 6 into 5, and then 4 factorial divided by 4 factorial into 5 minus 1 4 factorial, which will be equal to 24. So 4 factorial will cancel with 4, so 6 4 ja 24, 4 2 ja 8, so that is equal to 70. So therefore answer is 70 here. So let's continue with the next problem. The statement is there are 4 energy levels E, 2E, 3E and 4E, where E is greater than 0. The canonical partition function of 2 particles if these particles are 2 identical fermion. Okay, so let's first draw the various possible microstates which we can associate with the distribution of 2 identical fermions in these 4 different energy levels. So let me label these energy states. So 1, 2, 3 and 4. Okay, so energies are E, 2E, 3e and 4e. Okay, so because we will have various distributions, so I'm going to draw the requisite number of energy levels. Okay, in principle we require here 6 different configurations. Okay, 2, 4, 5, 6. Okay, this is the 6th one. Okay, now let's try to distribute these two identical fermions in these different energy states. Okay, because the particles, they are identical, so I will label one particle with the ball here. Okay, so that's the first possibility. The other possibility is first particle here and the second fermion here, first fermion here and the second here. Okay, now with respect to the second energy level, so suppose the first fermion is here, the second is here, first is here, and then the second is here. Now switch to the third energy level, here and here. These are the only 6 different possibilities. Okay, so let me now write the total energy associated with each microstate. So I will call this these as 6 different microstates. Okay, so we are having 6 microstates. Okay, so now the energy of each microstate. So here 2 plus 2e plus e, so the total energy of system is 3e. So here 1 plus 3e. Okay, so that is 4e. Here 1 plus 4e, that is 5e. 2 plus 3, 5e. Okay, so 2 plus 4e, 6e. 3 plus 4, so that is 7e. Okay, so therefore the partition function is given by z, that is equal to so we are having 2 microstates with same energy. Okay, so that means degeneracy for this case it is going to be equal to g, that is equal to 2. Okay, so let me write the partition function now. So I will continue from left to right. Okay, so the first term in the partition function, exponential minus 3 beta e. Okay, second term plus exponential minus 4 beta e. Okay, plus 2 times exponential minus 5 beta e plus exponential minus 6 beta e plus exponential minus 7 beta e. Okay, so therefore let me check which option is matching our result. So exponential minus 3 beta e plus exponential minus 4 beta e, and then exponential minus 5 beta e, it should be 2 times, and then exponential minus 6 beta e. So exponential minus 5 beta is only here, and then there's no exponential minus 5 beta e term here, and there's no exponential minus. So I think there's something wrong here. It should be there should be a factor of 2 here. Only then it's going to be a correct one. So therefore I will mark B as the correct one with this correction, slight correction. So there might be some typing error while while typing this question here. So what, there should be a factor of 2 here. Okay, with the energy state 5e whose degeneracy is 2. So therefore B is the correct option here. B is correct. So let's continue with the next problem. So again we are having the same system with 4 different energy levels. Okay, so let me draw these energy levels first, and then we'll come to the next part of the question. So the respective energies are E, 2E, 3E and 4E, where E is greater than 0. E is greater than 0. The canonical partition function of 2 particles is, so if these particles are 2 distinguishable particles, so we are having n is equal to 2 and the particles are distinguishable. So when the particles are treated as distinguishable, so that means we simply need to find the partition function for one single particle. So Z1, that is equal to sum over gi exponential minus beta ei. Okay, and because g it's 1 for all the energy states. Okay, so that means the partition function will be exponential minus beta e plus exponential minus 2 beta e plus exponential minus 3 beta e plus exponential minus 4 beta e, and the 2 particle partition function Z2 is equal to Z1 square because particles are distinguishable. Okay, so therefore this is nothing but exponential its whole square, that is exponential minus beta e plus exponential minus 2 beta e plus exponential minus 3 beta e plus exponential minus 4 beta e and its a whole square. So that's the partition function. So therefore option C is the correct one here. So let's continue with the last problem. The statement is, consider a gas of atoms obeying Maxwell-Boltzmann statistic. The average value of exponential iota a dot p over all moments p of each of the particle, where a is the constant vector and a is the magnitude, m is the mass of each atom, and t is the temperature, and k is the Boltzmann constant is. So we have to find the expectation value of the exponential iota p dot a. Okay, so the expectation value, we will make use of the definition of the expectation value of a physical quantity exponential. Here that physical quantity is iota a dot p. Okay, and by definition this is equal to, so we will make use of the Maxwell-Boltzmann probability distribution in one dimension, so minus infinity to infinity, so along three different directions from minus infinity to infinity, and then the physical quantity which is exponential iota a dot p here, and then f of px, f of px, f of py, f of pz, dpx, dpy, dpz. So in principle we can separate each individual x, y and z component. So here it should be noted that a dot p will yield us a dot p, that is equal to ax px plus ay py plus az pz. Okay, so now and also the f of px and f of px, f of px dpx, that is equal to the number of particles in the velocity range bx to vx plus dvx. Okay, that's a fraction of particle, basically not the number of particle but fraction of particle, and this is equal to 1 upon 2 pi m kt, where k is the Boltzmann constant here, and its power 1 by 2 exponential minus px square upon 2m kt dpx. Similarly, we can write exactly identical expression for the fpy dpy and fpz dpz. So I am not writing all those things here, but it's merely a replacement of the suffix here, and everything else will remain same. So now we can write the expression for the exponential iota a dot p, that is equal to, so I'm going to write the individual component for x and y and z momentum vector. Okay, so that is equal to, for the x direction 1 upon 2 pi kt power 1 by 2 minus infinity to infinity, and then exponential iota ax px. Okay, so when we will expand this, so we will have a three different terms. Okay, I'm writing the first term here. Now this 1/2 pi m kt, it is so m will be here. Okay, so this is from here. Okay, now this term exponential term into exponential minus px square upon 2m kt multiply by dpx, and then the next term 1 upon 2 pi m kt power 1 by 2 minus infinity to infinity, and then exponential iota a by py exponential minus py square upon 2m kt dp by and then the last term involving z component, 2 pi mkt power 1 by 2 minus infinity to infinity exponential iota az pz minus, sorry, not minus but exponential, for the exponential term exponential minus pz square upon 2mkt dpz. So I'm writing these terms as, all these terms as, I'm clubbing this 1 upon 2 pi mkt outside, so this is 1 upon 2 pi mkt, but it's a constant, so this comes out to be equal to 3 by 2, and then the remaining integral term, so minus infinity to infinity exponential iota ax px, okay, and then the other exponential term exponential minus px square upon 2mkt dpx, and then we will have the corresponding expression for the y dpy, okay, and then the corresponding expression for the dpz, okay, dpz. So I'm leaving this as equation 2, okay. Now I will call this as this constant as it is 1 upon 2 pi mkbt in its power 3 by 2 multiplied by I1, I2 and I3, where I1 refers to x integral and I2 refers to the y integral and z integral. Basically all these three integrals, they are exactly identical to each other, so I'm going to evaluate only one of them, and rest of the calculation will follow the same steps for the remaining two integrals. So let's evaluate I1 first, okay. So I1 can be rewritten as I1, that is equal to minus infinity to infinity exponential iota ax px, and then minus px square upon 2mkt and then dpx, okay. Remember that this is entire thing, this is in the exponent, so this is in the exponent, okay. Now this is equal to minus infinity to infinity and then exponential minus, now inside the bracket we will have its px square term, first px square, and then minus iota 2mkt into ax px, okay. So we will notice in a moment that why I'm multiplying here with 2mkt, and then what I'm going to do, I'm going to add a term and also subtract the same term, so that the net effect is 0, plus iota square mkt ax its square, and then I'm also subtracting the same term iota square mkt ax square, okay. This entire expression and this entire thing, it's divided by this 2mkt, okay, 2mkt. So when we will see now it's I think it's clear that why I multiplied here with the 2mkt. So 2mkt and 2mkt, they will cancel with each other, and then I will mean this term will be obtained, okay. So okay, now let's move to a further step. So this is equal to, this can be rewritten as, and yes, I forgot to multiply it with, it is dpx, okay. Now this is equal to minus infinity to infinity and then exponential minus, so minus px minus iota mkt ax square and then divided by 2m kt, and then we are having another constant term, this term basically minus iota square m kt ex square. So iota square will give us additional -1, so this will become minus, and minus that will become plus. Okay, and then we are having additional electric sign here in the outside. Okay, so exponential, this comes out to equal to exponential minus m kt by 2 ax square and then dpx. This is in principle equal to, I can keep this term outside, the term that I wrote at the end, exponential minus m kt by 2 ax square. I can keep it outside the integral minus infinity to infinity, and then exponential minus px minus iota m kt ax its whole square divided by 2m kt dpx. So let me call this as equation. So I have written equation 2, so let's call this as equation 4. Now here I'm going to make a substitution. Let px minus iota m kt ax, that is equal to by 1, so that dpx is equal to dy 1, and as px goes to minus infinity, by 1 goes to minus infinity, and as px goes to plus infinity, by 1 also goes to plus infinity. Therefore I1 is equal to minus infinity to plus infinity exponential minus by 1 square upon 2m kt dy 1, and then multiply by this quantity. Okay, exponential minus m kt by 2 ax square. This is a constant quantity in principle. Okay, on this integral, it's obvious that it is equal to here we are going to make use of the standard integral, that minus infinity to infinity exponential minus alpha x square dx, that is equal to under root pi by alpha. So if we make use of this integral, so that means this turns out to be equal to, so I'm writing this first, exponential m kt by 2 x square and then multiply by 2 pi m kt power 1 by 2. Okay, so let me call this as equation 5. Similarly, we can obtain that I2, that is equal to I3, that is equal to okay, so in case of I2 we will have ay square here, ay square, and in case of I3 we will have az square, and the rest of the terms will be identical. Okay, so for I2 I will have exponential minus m kt by 2 ay square, that's for I2, and then multiply by 2 pi m kt power 1 by 2, and for I3 we will have az square, and the rest of the terms will be similar. So therefore our final result is, let me introduce an additional page. So therefore our final result, that is I, that is I, or which is equal to the expectation value of, or the expectation value of exponential iota a dot p, that is equal to 1 upon 2 pi m kt power 3 by 2 I1 I2 into I3, I1 I2 and I3, and that is equal to 1 upon 2 pi m kt power 3 by 2, and then exponential minus m kt by 2, and then I will add all these terms, ax square plus ay square plus az square, and then the value of the three different integrals. That's 2 pi m kt. It is 1 by 2, so because there are three integrals, so that will be 3 by 2. Okay, so this will cancel with this one. So ultimately we are left with the expectation value of this quantity, that is equal to exponential minus m kt by 2 a square. So that is our answer. So let's see the options. So therefore option C is the correct one here.